Okay, so now that we know how to do dimensional analysis and conversions, we can go into the stoichiometry part of this, which is pretty much the meat and bones of what you're going to be doing for the first half of Chemistry 1. So first, I just wanted to go over the rules of stoichiometry real quick. I'm putting this at the beginning of the video, so if you need to refer to it, you can just go back to the beginning of the video and push play. This may not make too much sense to you right now, but as you see me work out the problems, they should start to make more sense to you. But let's go over this real quickly anyway, just as an introduction. So the rules of stoichiometry, so the way I have this set up, there's 5 different rules. So in the orange, if the question contains this in the orange, then what's in the white, you want to have this equality in your data table. You want to include this equality as one of the lines in your data table. So if the question is going to contain grams, if your question statement or your statement of inequality is going to include grams, then you want to include in your data table how many grams of that substance equals 1 mole of that substance. And if the question is going to include either atoms or molecules or ions, one of these 3, then you want to use Avogadro's number and set that Avogadro's number of that substance to 1 mole. And I'll go into Avogadro's number here in a minute. It's important you don't overthink this because students can get tripped up on Avogadro's number, but it's actually really straightforward. And of course, Avogadro's number is 6.022 times 10 to the 23rd. Now, if your statement of inequality or your question statement is going to include different compounds, if the question is going to have water on H2O on one side of the equal sign and OH on the other side of the equal sign or something like that, if they're going to be different compounds set equal to each other, you want to do it by their molar ratios. And if it has milliliters in the question statement, then you want to have a conversion factor of how many milliliters of that substance equals 1 liter. And of course, 1,000 milliliters equals 1 liter. And finally, if the question is going to have something to do with molarity, then you want to be able to have a conversion factor of how many moles of that substance is equal to 1 liter. Because remember, molarity is the number of moles of, whatever the salt is in 1 liter of water or 1 liter of solution. Okay, so if this doesn't make sense to you right now, don't panic. We're going to go through it and you'll see what I mean by these rules. And then for reference, you can go back to the start of this video and see this little summary and you'll have a better understanding of it. So the first example is how many moles of ammonia does 29.4 grams of ammonia contain? So how many moles of ammonia does 29.4 grams of ammonia contain? And ammonia is NH3, so you'll need to know that. So the question statement in your little data table that you're going to set up, we're going to, reading these word problems, as I said before, you're going to pull out the numbers and the question and make a little data table. So here's our data, here's going to be our data table. So the question is how many moles of ammonia? So question mark, moles of ammonia does 29.4 grams of ammonia contain. Now, if you notice, has the word moles in it in the question mark statement. So what you want to do is you want to set up how many grams of ammonia is going to equal 1 mole. So 1 mole of ammonia, and we need to find out how many grams of ammonia is in that 1 mole. So let's go to our periodic table real quick. And before we do that, let's just write this down. Ammonia is NH3, so you have N and you have 3 H's. There's N and there's 3 H's. So let's start with the N. Okay, now we're on our periodic table, and here is N right down here. And N has the atomic mass unit of 14.01. So let's go back to our problem. So N is 14.01 grams in a mole of N. Now we have 3 moles of H's here. So let's look up how many grams is in a mole of H. Let's go back to our periodic table. And here's H right here at the beginning. And that is 1.01 in 1 mole of H. So that's 1.01 in 1 mole of H. But there are 3 of them. So we have to take this number times 3. So 1.01 times 3 moles of H is 3.03 grams of H in 1 mole of H3. So we're going to take these and add them together. We're going to take the 14.01 grams of N, and we're going to take the 3.03 grams of H3, which is 1 mole of each, and we're going to add them together. So that's going to give us 17.04 grams total is in 1 mole of NH3. So we're going to write that in our data table. 1 mole of NH3 equals 17.04 grams of NH3. Okay, so now we have our data table set up, and we can proceed to dimensional analysis to find out this answer. Okay, so let's set this up. Now remember, when you're setting up your dimensional analysis, you always start with the line with the question mark in it, the how many. So how many moles of NH3 is in 29.4 grams of NH3? That's the question that we got from up here in the original problem. So we don't know, we have a question mark here. We don't know how many moles of NH3 yet, but we do know on the other side of the equal sign, we do know 29.4 grams of NH3, and we're just going to put that over 1. And then we're going to draw a multiply sign and a fraction bar. Now the very first unit of measurement that we have up here is grams of NH3. So we're going to put this diagonally opposite on the bottom of this next fraction bar, grams of NH3. And we're going to look up at our data table at the next line where it says grams of NH3. And that would be right here, grams of NH3. And how many do we have listed here? 17.04. 17.04. And whatever's on the other side of the equal sign, we're going to write on the top side of the fraction bar. So 1 mole of NH3. So 1 mole of NH3 equals 17.04 grams of NH3. Now we can go through, and we've used up this line in our data table, and we've tackled that line, and we're all done in our data table. So now we can go through and cancel out these units of measurement in our dimensional analysis. So since grams of NH3 is up here and diagonally down here is grams of NH3, those cancel out, leaving us just with moles of NH3 with nothing to cancel that out, so we have to leave that there. Now, is that the question that we're asking? Let's go back to our question mark. And our question is, how many moles of NH3? So we have moles of NH3 left over as the leftover unit of measurement, and the question is moles of NH3. So we know we set up the problem right. So now let's rewrite this so it's pretty. We just have 29.4 over 1 multiplied by 1 mole of NH3 over 17.04. Now we can just do our calculator and calculate across. 29.4 times 1 is 29.4, and 1 times 17.04 is 17.04. Now let's take our calculator and divide that out, and that gives us 1.725352113. And what's that unit of measurement we're going to carry down and put after this? Moles of NH3. So this is going to be our complete answer. 1.725352113 moles of NH3 is what is in 29.4 grams of NH3. Now with this, don't forget to round to sig figs, and in sig figs, since we're multiplying this, we're going to round it to the least number of sig figs that we have in our equation. The least number of sig figs is going to be 3, and that's from the 29.4, because as you can see, we have 29.4, that's 3 sig figs, and we also have 17.04, that's 4 sig figs. So we're going to use the least amount of sig figs, 3 sig figs. And if you don't not sure what I'm talking about, go and look at my video on significant figures and rounding. So that's 3 sig figs, so we're going to round to 1, 2, 3 sig figs. So let's draw this line. The number right after this line is 5, so that 5 goes back and turns that 2 into a 3. So you're going to end up having 1.73 moles of NH3 as your rounded answer. Now, Avogadro's number is, it's a constant number. This number does not change. It's 6.022 times 10 to the 23rd. If you have that number of atoms or ions or molecules of something, that is always going to equal 1 mole of that something. Now, as I said before, it's important not to overthink this. It's very straightforward. No matter what it is, it could be NH3, just like in the last example. If we have 6.022 times 10 to the 23rd atoms of NH3, that's going to equal 1 mole of NH3. If we have 6.022 times 10 to the 23 ions of NH3, that's going to equal 1 mole of NH3. And I know it seems like it might feel like you're skipping a step here, but it's just because this dude named Avogadro just already did the math for us and figured out that even if it's atoms or ions or molecules, if it's that number of that thing, that NH3, that is going to equal 1 mole of that same thing, that NH3. So if we have 6.022 times 10 to the 23 molecules of water, which is H2O, we're going to have 1 mole of water. So it doesn't matter what we're dealing with, what substance we're dealing with, or what compound we're dealing with. If it's atoms or ions or molecules of that thing, whatever that thing is, in this case it's water, it's going to always equal 1 mole of that same thing. Now we can't mix and match. We can't say 6.022 times 10 to the 23 atoms of NH3 equals 1 mole of water. That's mixing and matching the compounds. It has to be of water, that many molecules, ions, or atoms of water equals 1 mole of water, or that many atoms, ions, or molecules of NH3 equals 1 mole of NH3. So no matter what substance you're dealing with, if you have 6.022 times 10 to the 23 atoms, or 6.022 times 10 to the 23 ions, or 6.022 times 10 to the 23 molecules of a thing, is going to equal 1 mole of that thing, that same thing. These things have to be the same. Okay, so let's look at a problem and see how this plays out. So the question here is, how many moles of helium are in 7.26 times 10 to the 24th atoms of helium? So don't panic. We're going to notice that it says atoms of helium, and that should automatically set off a little light for us. Ding, 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 ding. We need to use Avogadro's number. So let's first start with our data table, just like we do with anything, and we start with the how many. How many, question mark. How many what? How many moles of helium? So how many moles of helium are in 7.26 times 10 to the 24th atoms of helium? So now, since we know we need to put an Avogadro's number in here, line in here in the data table as a conversion factor, and Avogadro's number is 6.022 times 10 to the 23rd, we're going to put 6.022 times 10 to the 23rd atoms of helium is going to equal 1 mole of helium. And it's as simple as that. So now we can set up our dimensional analysis, and we start with the question mark line. We start with what's on the other side of the equal sign, what we know, which is 7.26 times 10 to the 24th atoms of helium, and we just set that over 1. Multiply fraction bar. Now the unit of measurement we have on the top of here is atoms of helium, so we're going to put that on the bottom of our next fraction, atoms of helium. Now we're going to look down up at our data chart, and we're going to find out where else it says atoms of helium, which is this Avogadro's number. So we're going to put 6.022 times 10 to the 23rd atoms of helium, and whatever's on the other side of the equal sign, 1 mole of helium goes on the top of the fraction bar. 1 mole of helium. So we're going to cancel out our units of measurement that can be canceled out. So we have atoms of helium on the top here, atoms of helium on the bottom here. They cancel each other out, leaving us with moles of helium. Now let's look up at the question. Is that what it's asking? Yes, question mark moles of helium. So we know we set it up right. So now we can just multiply across 7.26 times 10 to the 24th times 1 is 7.26 times 10 to the 24th moles of helium. And then on the bottom of the fraction, we have 1 times 6.022 times 10 to the 23rd equals 6.022 times 10 to the 23rd. Now we just plug this in our calculator. 7.26, and you're going to hit the little E button on your calculator. That means times 10 to something. And you're just going to hit E24. And then hit the dividing bar, or the dividing sign. And then 6.022 E23. And that's going to give us 12.05579.542 moles of helium. Now, if you were following along with me and you understand this, but somehow, and you got the 7.26 times 10 to the 24 moles of helium divided by 6.022 times 10 to the 23, but you did not get this number, this 12.055, then you just entered it in your calculator wrong. And so that's, I'd have to save that for another video on how to enter it into your calculator. But this is the answer that you get when you plug it into your calculator correctly. And then we need to round down to sig figs, to the least amount of sig figs. So we have 3 sig figs right here, 7.26, and we have 4 sig figs right here, 6.022. So we're going to choose the least amount of sig figs, which is 3. So we're going to round this to 1, 2, 3, 12.0, but that next number after the 12.0 is a 5, so that's going to come back and change that into a 12.1 moles of helium. And that's your answer. So the next problem is a sample of water contains 42.718 moles of water. How many molecules of water are in this sample? So first we're going to go for the how many, because that's going to be our question mark. So how many molecules, and this is the abbreviation for molecules, of water are in this sample? Well, what sample? The sample of water that contains 42.718 moles of water. So 42.718 moles of water. Now, since this says molecules on it, your question mark includes molecules. How many molecules? That should set off alarm bells for you. Ding, 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 ding. And we need to use Avogadro's number, which is 6.022 times 10 to the 23. So 6.022 times 10 to the 23, 10 to the 23 molecules of water is just going to equal 1 mole of water. And it's that simple. And so see how in these past 3 examples, regardless if you have atoms or ions or molecules, it's all going to be the same. It's all going to be 6.022 times 10 to the 23rd, either atoms, ions, or molecules of the substance, in this case water. They all equal 1 mole of that substance. They all equal 1 mole of water. So now that we have this set up, we can do the dimensional analysis. So we start with our question mark statement, 42.718 moles of H2O over 1 times fraction bar. And the unit of measurement on the top we wrote was moles of H2O, so we're going to write that on the bottom. And we're going to look at the next data line. And here's moles of H2O, that's just 1. So whatever's on the other side of the equal sign, we're going to put on the top of the fraction bar, which is the 6.022 times 10 to the 23rd molecules of water. Now, we can cancel out any units of measurement that are diagonally across from each other. So we have moles of H2O up here, moles of H2O down there, leaving us with molecules of H2O. Now, is that what the question's asking? Yes, molecules of how many molecules of H2O? So we set it up right. So now we just need to multiply across. So 42.718 times 6.022 E23, that's on your calculator, the button E, and that's going to equal 2.572477796 times 10 to the 25th. And then on the bottom of the fraction, that's just 1 times 1, so that's just going to be 1. So now we need to count sig figs so we know how short to round this answer. So this one is 1, 2, 3, 4, 5 sig figs. And this number is 1, 2, 3, 4 sig figs. So we're going to round this to 4 sig figs. So if we round it to 4 sig figs, that's 1, 2, 3, 4. And this 4 over here doesn't affect the 2 at all. So our rounded answer is just going to be, and that wavy equals sign means about, means it's been rounded, 2.572 times 10 to the 25th molecules of H2O. And that's your answer. So a chemist weighed out enough sodium chloride so there were 8.395 times 10 to the 23 ions of sodium. How many grams of sodium were in this sample? And sodium chloride is NaCl. Now this is a little bit more complex in the fact that it has more layers to it, but don't worry, that complex does not mean it's more complicated. We're going to do the same thing that we've always done, and we're going to make our data table first. So data table, and we're really going to read this problem and find out what it's asking. A chemist weighed out enough sodium chloride, so there were 8.395 times 10 to the 23 ions of sodium. So 8.395 times 10 to the 23 ions of sodium. And look at that ions. So if you see the word ions, that should ring bells for you that we're going to probably be using Avogadro's number, which is 6.022 times 10 to the 23. So back to the data table, we have 8.395 times 10 to the 23 ions of sodium, which is Na. And then how many grams of sodium, so equals how many grams of sodium were there in the sample. So we have our initial question mark statement, 8.395 times 10 to the 23 ions of sodium equals how many grams of sodium. And we know we need to use Avogadro's number because it has the word ions in it. So 6.022 times 10 to the 23 ions of sodium is going to equal what? Is going to equal 1 mole of sodium. So you might be saying at this point, but we're talking about sodium chloride. It says sodium chloride, right? And sodium chloride is NaCl, so where does the NaCl come in? Well, that's just extra information that's getting put into this problem that you don't need to worry about. We're just going to let that fall off to the side, because what the question is how many grams of sodium. It says nothing about sodium chloride. It says how many grams of sodium were in this sample. And when they weighed out enough sodium chloride, it gives us the 8.395 times 10 to the 23 ions of sodium. So we have the sodium equivalency that we need to find out. And so the chloride really is irrelevant. So we don't have to worry about the chloride and sodium chloride in this problem. They just gave it to you because this is a real life lab situation. But you need to be able to discern when the information is not needed to solve the problem. And another check that you can do when we do our data table, when we're finished with our data table, there should be 2 mentions of everything. So right now, let's check and see if we have 2 mentions of everything. We have ions of sodium here and ions of sodium here. That's 2. We have grams of sodium here, but we don't have another mention of grams of sodium. And we have moles of sodium here, but we don't have another mention of moles of sodium. So we're not finished with our data table. Now we need to find, we need to write another equivalency converting grams of sodium into a mole of sodium, and that should complete our data table. So we need to find out how many grams of sodium equals 1 mole of sodium. So let's look at our periodic table. And sodium is right down here, and that's 22.99. So let's go back to our data table. So 22.99 grams of sodium is going to equal that 1 mole of sodium. Now we can go back and check. There are 2 mentions of ions of sodium. There's 2 mentions of grams of sodium, 1, 2, and there's 2 mentions of moles of sodium. So now that we see that there's 2 mentions of everything in our data table, now we can go ahead and set up the dimensional analysis and solve the problem. So of course we start at the question mark statement. So 8.395 times 10 to the 23rd over 1, and this is ions of sodium, multiply sign, fraction bar. Now our unit of measurement we have up top here is ions of sodium, so we're going to write that down here on the bottom, ions of sodium. And we're going to look up at our data table and find another mention of ions of sodium, which is this next line right here. 6.022 times 10 to the 23rd ions of sodium. And on the other side of the equal sign is 1 mole of sodium, so that's what we put on the top of the fraction bar. And then we make another multiplication sign and another fraction bar. Now the unit of measurement on the last fraction that we just wrote on the top of the fraction is moles of sodium. So we're going to bring that down, and we're going to put that down here opposite on the bottom, moles of sodium. And we're going to look up at our data table and find out where else it mentions moles of sodium, which is this third line right here. 1 mole of sodium equals 22.99 grams of sodium. So we have 1 mole of sodium, and on the top we do the 22.99 grams of sodium. And now we can cancel out all of our units of measurement that are diagonally across from each other. So we can cross out ions of sodium, moles of sodium, moles of sodium. And what we're left with is grams of sodium. Now let's check back up with our question mark. Is that what they're asking? Yes, they're asking how many grams of sodium. So we know we set it up right. So let's take our calculators and multiply across 8.395 times 10 to the 23 times 1 times 22.99. So the top of the fraction bar is 1.9300105 times 10 to the 25th grams of sodium. And then we multiply across on the bottom of the fraction bar, so we multiply the 1 times the 6.022 times 10 to the 23rd times 1. So that would equal 6.022 times 10 to the 23rd. And our answer we end up getting is 32.04932747 grams of sodium. Now we need to go back and round to sig figs. So in this first set of numbers, 8.395, this is 4 sig figs. And then over here for Avogadro's number, we have 4 sig figs, 6.022. And up here on the very last fraction, we have 22.99. That's 4 sig figs also. So we're going to round this to 4 sig figs. So 1, 2, 3, 4. But that 9 changes this 4 into a 5 when you're rounding. So we're going to end up with 32.05 grams of sodium. And that's your answer. So the next problem is how many moles of hydrogen gas are required to produce 103.7 moles of ammonia from the following balanced equation. So let's look at this balanced equation for a minute. We have 3 moles of hydrogen gas. Hydrogen gas is H2. And hydrogen gas always comes in the form of H2, just so you know. So we have 3 moles of hydrogen gas, of H2, plus 1 mole, because there's nothing here, so 1 is implied, of nitrogen, of elemental nitrogen, or nitrogen gas, yields, and that's the yield arrow, yields 2 moles of ammonia. And ammonia is this NH3 altogether. That's ammonia. This is hydrogen gas. So how many moles of hydrogen gas? There's our question mark statement. So let's write this down in the data table. How many moles of hydrogen gas are required to produce 103.7 moles of ammonia? So 103.7 moles of ammonia, and ammonia is NH3, from the following balanced equation. Now notice it says balanced equation, because you couldn't do this unless the equation was balanced. You'd have to balance it first if it was not a balanced equation. So here is our question mark statement. And it looks a little bit different than what we've been doing because if you notice, the substance on one side of the equal sign is completely different than the substance on the other side of the equal sign. See, the substance on this side of the equal sign on the left is hydrogen gas. The substance on the right of the equal sign is ammonia. So when we're dealing with two different substances on either end of the equal sign, we have to go back to our rules of stoichiometry and we have to use the molar ratio. Molar ratio. And what I mean by the molar ratio is let me change colors here. What I mean by the molar ratio is that for every 3 moles of hydrogen gas, that's going to yield 2 moles of ammonia. So we have a 3 mole of hydrogen gas to a 2 mole of ammonia ratio. So we need to put that and include that in our data table. We need to actually say 3 moles of hydrogen gas is going to be equal to 2 moles of ammonia. So that's what I mean by the molar ratio. For every 3 moles of hydrogen gas, 2 moles of ammonia is made. So let's look and see if we need anything else in our data table. The question is, how many moles of hydrogen gas are produced by 103.7 moles of ammonia? So let's count and see if each of these are mentioned twice. So we have moles of hydrogen gas, that's mentioned once, moles of hydrogen gas, that's mentioned twice, and then we have moles of ammonia, that's mentioned once, and this is moles of ammonia. I wrote it down differently, but it's the same thing. I'll erase this and write it down the same way so it's not confusing. 2 moles of ammonia. So that's the second mention of moles of ammonia. So our data table is complete because we have 2 mentions of each thing in our data table in the equivalencies. So now we can set up our dimensional analysis and solve. So of course we're going to start with the question mark statement, and we're going to start on the other side of the equal sign what we know, which is 103.7 moles of ammonia. So 103.7 moles of ammonia over 1, and then multiply in a fraction bar. And the unit of measurement on top of that fraction is moles of ammonia, so we're going to write the moles of ammonia down here. And we're going to look and see where else moles of ammonia is mentioned. That is on the second line over here on the right. So and that's 2 moles of ammonia. So 2 moles of ammonia. And whatever is on the other side of that equal sign, 3 moles of hydrogen gas goes on top of the fraction bar. So now the next thing we do is we cancel out the units of measurement that can be canceled out. So we have moles of ammonia right here, and diagonally across from it is moles of ammonia. So we can cancel those out, leaving us with moles of hydrogen gas, of H2. Now if we go back up and look at the question, what is the question asking? Question mark moles of H2. So we know we set it up right because that's the unit that we have left over. So now we can just go across and multiply across. 103.7 times 3 is 311.1 moles of hydrogen gas over 1 times 2 is 2. So now we need to take that 311.1 and divide it by 2, and that's going to get us 155.55 moles of hydrogen gas. Now let's go back and check for sig figs to see if we need to round this down at all. First we have 103.7, that's 4 sig figs. And then everything else is just the number of moles. So 3 moles, here's 3 moles, here's 2 moles, 1. So you don't count it when it's just one number with no decimal or anything after that, when it's just one, the number of the moles. That doesn't count in the sig figs. The only one that we count is this 103.7, which is 4 sig figs. So we need to round this down, this 155.55 to 4 sig figs. So 1, 2, 3, 4. This 5 turns the 5 into a 6. So we have rounded down 155.6 moles of H2. And that's your answer. Now, what is the molarity of a solution created by dissolving 25.73 grams of sodium chloride into enough water to make 750 milliliters of solution? And sodium chloride is NaCl. So what is the molarity? They're saying molarity in this one. Now remember, molarity is abbreviated by a capital M, and the molarity is the number of moles of the salt or of whatever you're putting in it out of a total of 1 liter of solution. That's molarity. And this 1 liter never changes. I know it says up here 750 milliliters, so we're going to get to that. But a molarity is specifically the number of moles over 1 liter. Just like when you're driving the speed limit, if you're driving down the highway and the speed limit says 60, they mean 60 miles per hour. So 60 miles per 1 hour. This 1 hour never changes. If the speed limit changes to 35 miles an hour, then that's 35 miles per 1 hour. See, this 1 hour never changes. It's always per hour. Just like that, just like the speed limit, the molarity always is per 1 liter of solution. So let's continue on with this problem and see how to solve it. Now, what is the molarity of a solution created by dissolving 25.73 grams of sodium chloride into enough water to make 750 milliliters of solution? So we're going to dissolve 25.73 grams of sodium chloride into enough water to make 750 milliliters of solution. And we want to know what is the molarity. So what it's asking is, what is this number? How many moles? What's the speed limit? How many miles per hour can you go down the highway? So how many moles in 1 liter if we have 25.73 grams of sodium chloride and 750 milliliters? So what it's asking, here's the question mark, is how many moles are in 1 liter? So we're going to write how many moles of sodium chloride is in 1 liter of solution. So we also need to know, since we are dealing with grams in this, we have grams of sodium chloride, but what we need to know is moles of sodium chloride. So we need to know how many grams of sodium chloride makes up 1 mole. So 1 mole of sodium chloride is going to equal a certain amount of grams. And how do we do that? Well, we have sodium chloride, which is NaCl. So let's go to the periodic table and find out how many grams per mole each of these elements are. Let's start with sodium. Okay, so sodium is right here. And this sodium is 22.99. So let's go back down to our problem and write this 22.99 grams of sodium is 1 mole of sodium. Now we need to find out chlorine. How many grams of chlorine is in 1 mole of chlorine? So let's go back up to our periodic table, and chlorine is in this row down here, and that's 35.45. So let's go back down to our data table, and chlorine is 35.45 grams per mole. So now we need to add these together. So 22.99 plus 35.45 equals 58.44 grams of sodium chloride equals 1 mole of sodium chloride. So let's put that in our data table. So we have the 1 mole of sodium chloride already written out. So that equals 58.44 grams of sodium chloride. Okay? Now, let's see if we have everything we need in this data table, if everything's mentioned twice. We have grams of sodium chloride up here and grams of sodium chloride down here. So that's twice. We have moles of sodium chloride right here and moles of sodium chloride right here. So that's twice. But look, we have 1 mention of liter and 1 mention of milliliter. So we need to remedy that by adding another line in our data table. So we need to remember that 1,000 milliliters is equal to 1 liter. So now when we look at this, we have the 750 milliliters, that's 1 mention of milliliters, and then we have the 1,000 milliliters, that's the second mention of milliliters. And then up here we have 1 liter, that's 1 mention of liters, and down here we have 1 liter, that's the second mention of liters. So now our data table can be considered complete because everything is mentioned in it twice. And we can go ahead and set this up and solve using dimensional analysis. So we start with the question mark statement, which is how many moles of sodium chloride equals 1 liter. So we have 1 liter over 1, and then times and a fraction bar. And then we want to put this liter unit of measurement on the bottom. And the other place that a liter is mentioned is way on the bottom of the data table on the right, another 1 liter. So 1 liter down here. And what's on the other side of the equal sign is 1,000 milliliters. So 1,000 milliliters. Then we want to put another multiplication sign and another fraction bar. And we left off with milliliters on the top, so we're going to put milliliters on the bottom. The next place in the data table that milliliters is mentioned is over here, 750.0. and what's on the other side of the equal sign is 25.73 grams of NaCl. Now we do another multiplication sign and another fraction bar. We left off with grams of NaCl. And so where else is grams of NaCl mentioned? On this third line in the data table, this 58.44. And whatever's on the other side of the equal sign, 1 mole of sodium chloride goes on the top. So we've used up all of the lines in our data table. So let's cancel out all of the units of measurement that we can cancel and make sure that we set it up right. So we have liter here, milliliters up here, milliliters down there, grams of sodium chloride up here, grams of sodium chloride down there. And we're left with 1 mole of, or we're left with moles of sodium chloride, which is exactly what the question mark is asking. How many moles of sodium chloride is in 1 liter? So now we can get our calculators out and we can just multiply across. So we're going to go 1 times 1,000 times 25.73 times 1, and that's going to equal 25,730 moles of sodium chloride over, and we'll multiply across on the bottom. We have 1 times 1 times 750.0 times 58.44. So the answer to that is 438.30, 43830. Now all we need to do is divide this out. So 25,730 divided by 43,830 equals 0.58704084 moles of sodium chloride. Now, we need to go back and look at the sig figs and round this down to the appropriate sig figs. So, sig figs, we had 25.73, so that's 4 sig figs. We had 750.0, so that's 4 sig figs. We start at the 5, the 0.5870, and that would be 4 sig figs moles of NaCl. Now the question, I know the question asks what is the molarity, but the way we did it is we figured out how many moles is in 1 liter, because look at the question mark statement. The question mark statement is how many moles of sodium chloride is in 1 liter. So that's what molarity means. The number of moles of the sodium chloride in 1 liter. That's what the molarity is. So we would just write it, instead of 0.587 moles of sodium chloride, we would write 0.587 molarity, capital M, of sodium chloride. So it would be 0.587 M is the molarity of the sodium chloride solution. So now that we've worked through these and we've gone over Avogadro's number, let's go back to the rules. Let's go back to the rules and review these rules that I introduced at the very beginning of the video, now that you've seen examples of it. Now see, in these stoichiometry rules, every time there was grams mentioned, we found out how many grams of that substance
equaled 1 mole of that substance, and we included that in the data table. Anytime atoms, molecules, or ions were mentioned, we used Avogadro's number and set that equivalent to 1 mole of that substance. So 6.022 times 10 to the 23 atoms equals 1 mole of atoms of whatever, of sodium, say, equals 1 mole of sodium. 6.022 times 10 to the 23 atoms of oxygen equals 1 mole of oxygen, and so on. Now, with every time there was different compounds on either side, because remember we had hydrogen gas on one side of the equal sign and ammonia on the other side of the equal sign, we used molar ratios. For every so many moles of hydrogen gas, so many moles of ammonia was made. Every time we saw milliliters, we had to include that conversion factor of 1,000 milliliters equals 1 liter. And every time the word molarity was brought up, we had to ask the question, how many moles of that substance would be in 1 liter? And so that's how you do these rules, and that's why I started off with the rules just to set the tone, and that's why we're reviewing them now that you've gotten a chance to see them in action. If you want to go back to the beginning of the video, you can review these rules at any time or write them down on a piece of paper or take a screenshot of them just to memorize them. But when you get into making the data tables, they really kind of make sense and they remind you on their own to go ahead and do it. The only thing you need to really remember is what molarity means. First of all, molarity is a number of moles in 1 liter of a substance. And you also need to memorize that atoms, molecules, or ions require the Avogadro's number conversion included in your data table. Okay, so I hope that helps, and I will talk to you later and ask me if there's any questions.